Welcome to day 8 of the Advent of Code. Today we're going to debug a program written in a minimalistic assembly language. And here you can see my own little tiny example. So the language only consists of 3 instructions: egg, knob, and jump. The instruction consists of an operation and an argument, and let me explain with this example what it means. So the virtual machine on which we execute this program only has a single global variable called accumulator. And the first instruction here, accumulator plus 2, means add 2 to the accumulator, which started out as 0. So here we incremented from 0 to 2. Then we incremented from 2 to 5, then from 5 to 10. And then the knob instruction doesn't do anything, and the plus 3 is simply ignored. And then we increment the accumulator from 10 to 17. And then we jump back in the program 1, 2, 3, 4, 5 instructions. And then the virtual machine says, hey, I already executed this line. It seems like we have an infinite loop. I'm going to stop and return the value of the accumulator. Okay, so first of all, we have to be able to parse these instructions. Okay, so let's play around with them a bit. For example, let's say, what about our good old friend, the rematches function? So what is a good regular expression that describes these kind of instructions? So we could say first we want an accumulate or a jump or a knob. Then we want a space, and then we want a number, but the number is prefixed by either a plus sign or a minus sign. Okay, cool. And then we get the entire match and the first subgroup and the second subgroup. That's looking good. Does it also work for negative numbers? Yeah, looking good. Okay, cool. So maybe let's use this in a let binding. So this would be an instruction. And as I already said, an instruction consists of an operation and an argument. Okay. And of course, the first match isn't important. So let's align it again, as I like to do. Right, like this. And then let's see if we did the right thing. Yeah, here now we have a result vector with a string and another string. And I would like to turn the first string into a keyword. That's just more idiomatic in Clojure. And I would like to pass the second string into an int by parsing it. Yeah, that's looking good, keyword and int. Maybe let's do it like this. Okay, cool. So that's already the parsing of the instruction. Let me take this input and comment it so I understand it tomorrow. And here's our output. Okay, and then let's abstract into a function. Let's say, whoops, parse instruction given the serialized form, and then replace this guy with the serialized form. Okay, now we have our nice parse instruction function. Okay, so how would we now parse multiple instructions? Maybe let's move these guys down like this. Right, so let's start with this example, and then note when I press the enter or the tab key, unfortunately my IDE indents within multi-line string literals. That's not so nice. I have to fix that sometime. Okay, but first let's say we want to split the lines, which is a nice function which splits on an optional R and then an N. So on Windows systems you have this carriage return before the line break, and on Linux and Mac you only have this new line. Okay, so now we get a vector of those lines. Right, and now here we have our unfortunate white space. So if I now pass those strings as instructions, we probably get some error. Yeah, that's not so good. So first let's maybe trim those strings. So the leading and trailing white space is removed. And of course I have to map that function so it works on all the strings. Yeah, that's looking good. Okay, cool. So I think now we are ready to execute the program, but of course we don't have an execute function yet. So maybe let's write that next. So we want to execute a program which is a vector of instructions. Maybe I should make this clear. Let's get rid of the execute again and provide the example. Maybe let's just take this example. Okay. Input like this, and the output would be something like 17, for example. Okay, cool. And then let's put the execute back so we don't forget it later. Okay, so how do we write our own virtual machine? We have to think about the state that the virtual machine needs, and we're probably going to loop, and let me do that with an imperative loop. So Clojure has a loop macro that at first glance looks like a let statement, so we have to provide initial bindings. So the state of our virtual machine. So first of all, the accumulator starts at 0, and then the program counter or the instruction pointer has to remember which is the next instruction, or where is the next instruction that I have to execute. That would also be 0 at the beginning of the program. And then we have to remember which lines we already visited, right? So we use an empty hash set for that initially. Okay, cool. Now let's check if the program counter is in the visited set. So if we already executed this line, so that would be contains visited program counter. And if that is the case, what do we want to do? We want to return the accumulator. Okay, and otherwise we have to execute the instruction. How do we do that? So let's say the next instruction would be program PC. And you might be wondering, why can I use a vector as a function? What does it mean to call a vector with a single argument? Let me show you. Or maybe let me show you later. For now, let's just accept that. I will show you at the end why that works. Okay, cool. And of course, we know that the instruction is made up of an operation and an argument, so we can immediately destructure that. Okay, cool. Now let's maybe do a simple case analysis over the operation. So we have to do something for egg, jump, or nop. Okay. And what do we want to do? We want to jump back to line 24, basically, right? And we do that by providing new bindings for egg, PC, and visited. Okay, so the accumulator increments by the argument, right? Then the program counter is simply incremented. We want to execute the next instruction afterwards. And then the new binding for visited would be conj onto visited the program counter. Okay, and note that this is the old program counter, right? We're in a functional language. This doesn't change PC. It just gives us a new value that's one bigger. Okay, cool. So now what do we want to do for jump? The accumulator doesn't change by the jump instruction. And since argument is a relative offset, we simply add that to the program counter. Okay, and then the visited is exactly the same, right? That will be the same for all three cases. Okay, and nop doesn't change the accumulator. It increments the program counter, and here again we do this. Okay, cool. I think that should already work. Let's see. Okay, duplicate test, constant PC. Where is the bug? Okay, let's see if I find it myself. Oh, I did. Okay, I forgot to call the actual function that, or the special form that jumps back to line 24. Yeah, okay. So this is a special form. It jumps back to the innermost function or loop. Okay, cool. Now let's see if we can execute the program. We would expect 17. Okay, lazy seek. Okay, so the problem is here I told you program is a vector, and that's why this function call works. But of course, map gives us a lazy sequence, and we must turn that into a vector for it to work. Okay, interesting. So now we have our result 17. Very nice. Okay, so then let's see if that works for the real input. I already provided something here. So here's the real input, quite a long program. You can see here multi-digit numbers going up to hundreds. So the program is quite a lot larger than my example. Okay, so again, let's map the pass instruction function over it, fuse the map with the vec. And let's see if that works. Okay, and then let's execute the program. And we get 1867. That's the correct result. That works. Cool. So that was part 1. Find the accumulator at the point where we detect an infinite loop. Okay, so part 2 is, can we fix the infinite loop by changing a knob to a jump or a jump to a knob? And in this example, both cases would work. So let's start with this one. So if we jumped 3 forwards, that would be 1, 2, 3. Then we're at the end of the program and we can terminate. That's legal. Okay, and here if we changed the jump -5 to a knob -5, we wouldn't do anything here, reach the end of the program, and then we would be happy. And still we would have to return the accumulator. So that's an interesting problem. Let's see. So yeah, so maybe let's introduce. Oh, that's interesting. So what would happen if we access the program beyond its end? That should give us an exception, right? So maybe let's not fix the execute function for now. Let's stay with the main code here. Okay, so let's say this is our program. Okay, and maybe let's save that in a let binding. Let's say program should be that guy. Did I do that right? Yeah, that's still our program. Okay, and now if we count the number of instructions, if we count the number of instructions, we get 644. Okay, so there are 644 possible places where we could change an instruction. So maybe let's build a range that contains the numbers from 0 to 643. Here you can see the beginning of that range. And then let's map that range so that it updates the program at those specific indices. And before we do that, let me show you 2 functions related to updating. Let's say I have the first 4 odd numbers in this weird nested format. Okay. And let's say I like primes better than odds, so I would like another version of this vector where the inner vector has a 2 at the beginning instead of a 1. Okay, how would I do that? I can use the update function. I pass it the odds and then index 0, and then a function that, given this vector, returns a new vector with 2 and 3. So I can basically call update again, right, on the argument, and then say at index 0, where the 1 currently is, I want to increment that number, and then we get a 2 at that index. Okay, but that's first of all, we didn't change the odds vector, of course. Clojure has immutable collections, but this is not very nice syntax, right? So let me show you an alternative. That's the update in function, where I provide the odds and then a vector of indices, those zeros from above, and then I want to increment, and that works just as well. And it's a much nicer syntax, especially if this vector gets larger, if your nestings go down to 3, 4, 5, and so on. Okay, cool. So why is this interesting for us now? Because we want to update our program at those indices, right? So basically now I want to generate 644 different programs that only differ from the original at one index. Okay, let's see if we can if we can do it. So we want to map those indices with a function that uses our update in on the program. And what's the access vector that would be the index that is contained in the lazy sequence, and then the index 0 because that's where the operation is. 1 is the argument and 0 is the operation. Okay, and now we need a function that maps jump to knob, knob to jump, and egg to egg. And we can use just a map literal for that. I could say jump maps to knob, knob maps to jump, and ACC maps to ACC. Right? This is a perfectly valid function that given jump will return knob, given knob will return jump, and given ACC will return ACC. Okay, so let's see what happens if we execute this. Right, now we get lots of programs. Maybe what happens if I do it like this? Okay, that's also not very visually appealing. Maybe if I do it like this. Yeah, here you can see. So the ACC didn't change at all. The jump was changed to a knob. The ACC didn't change. The ACC didn't change. The jump was changed to a knob. So on this diagonal, you will see the changed operations. Okay, cool. So now we want to execute all those programs. Okay, and we don't get any exceptions. That's interesting because I predicted that here we should get an exception when we reach the end of the program. And that's because by default, the REPL will only print the first 100 elements. So the first 100 modifications didn't give us a terminating program. So if I now force the evaluation with a run print line again, then we will see that sometimes we get different results. That's quite interesting. And, there's another different result. And if I keep scrolling, we should get an exception sooner or later. There it is. Here, index out of bounds exception in line 26. So that's exactly the line that I predicted. So we have to protect against that. So let's say, let's introduce another if. So if the program counter is at the end of the program, then, this belongs here. If it's at the end of the program, then we want to return the accumulator as well. Okay. And then the exception should be gone, but we won't be able to distinguish these cases. Let's see if the exception is gone. Yeah, okay. Okay, so now how do we distinguish between these two cases that both return the accumulator? Let's simply return a more involved result. So maybe let's say we will return status loops and then accumulator 17, something like this. So that would be this case here, where we say the status is loops and the accumulator is the accumulator. And here we can say status halts, accumulator is accumulator. Okay, so then we should be able to distinguish those cases. Let's see if we execute how this now looks. Yeah, here you can see it with pretty printing. All those guys loop, and somewhere down the road we hopefully will have a halt. Let's see if we can find it by filtering, where halts is the status of our argument. Yeah, and there we are, accumulator 1303. And then, in case the result is too noisy for you, we can even access the result at the accumulator. Oh, no, we can't, because right, we have a sequence. We know there's only one result, right? And then we can access with the accumulator keyword. Okay, cool. Right, so let's see what we learned today. Right, so this is again ordinary regex parsing, nothing interesting there. So we learned about the loop recur construct, where we can provide initial bindings after the loop and then new bindings with the recur special form. Oh, right, one thing that I didn't show you. So when we always pass the same value for conch visited PC, we can make our program a little bit shorter and say, let's simply put that in the let binding and say visited is conch visited PC. Then we can replace these guys with visited and make it a little bit shorter. So this won't change the existing visited binding. It will provide an inner binding that shadows the outer one. But that's an established idiom, so we can't accidentally access the old value of visited or the value of the shadowed visited. Okay, so that's loop recur. Then we learned that we can use vectors as functions, and I wanted to show you that why that works exactly. So here's a vector, and if you right-click on Clojure lang persistent vector, you can see what are the classes that we extend and what are the interfaces that we implement. The list of interfaces is very long, so let me right-click on the abstract function class. Here we can see the abstract function class implements the interface for functions, and this is basically the Java method that will be called when you use a vector as a function, right? So the single parameter here will be the index that we pass, in our case PC. Okay, so that's what happens under the hood. Okay, and then here we used a map as a function. Again, if I take an arbitrary map, in this case a persistent array map, but for larger maps that would be a hash map. Both of them work. Shouldn't hash map give me a hash map? Huh, that's interesting. Okay, anyway, works for both of them. Again, we extend abstract function, we implement interface function, and then basically the same method is called, and the key is then passed in. Okay, cool. And the rest, oh, here, and keywords are also functions. That's also interesting. So let me show you any keyword, doesn't really matter which one. That's a keyword. And keywords implement iFunction. That's even the first interface they implement, right? And they take a map and they look themselves up in the map. So that's very useful. If you want to map keywords over sequences, then they will look themselves up in the given map. Okay, so I think this was a quite interesting exercise, and I hope it gets even more interesting in the following days.